All right. So what we're going to be looking at now is circular motion. What do you think circular motion is?
A motion that like involves like some like to being a circle, something.
Basically, it's
Like,
motion in a circle, as the name might suggest. So in this case, we've got a circle here. If you've got a particle that's moving along this circle in a circle, then it's undergoing circular motion.
yeah.
Now, before we do some calculations of circular motion, we understand it moves in a circle, but we need to sort of think about a few things here. If you've got a particle and it starts at some location, let's say A, and it gets to some point B, then we know that this means that it's gone from here to here. So the displacement will be in this direction. Yes?
Yeah.
And the velocity will be in which direction? From A to B. The
Also that.
also in this direction.
Yep.
Now, that's the velocity and displacement from A to B, which takes some time, yes?
Yeah.
But so that's the average velocity.
Yep.
But to get there, I went along this curve. I didn't go in a straight line. So
Yep.
if I want to get the instantaneous velocity at A, how do I do that? How do I get instantaneous velocity?
Like at any point.
Yeah, well, I mean, we want it at A as an example, but in general, at any point.
Probably like you probably need like some like formula that's part like the sum circle formula or something. I'm not sure.
No. So I think you're overthinking it. Go back to module 1. Velocity is displacement over time, yes?
Yeah.
And the average velocity over some time period, no matter how the particle moved, is the total displacement over that time period divided by the total time period, yes?
Yeah.
Now the velocity can change. So if I want a better approximation of my velocity at a particular point in time, I might take a shorter period of time, yes?
Yeah.
So I might go from A to B prime. And that means this yellow direction will give me a closer approximation to, well, it will give me the direction of the velocity over this period of time, yes, from A to B prime, which is a shorter time from A to B compared to A. And so that gives me a closer idea of the direction and magnitude, if I were to do the numbers, of the velocity at A, right?
Yeah.
And I could, of course, take an even shorter one to B double prime. Now, as I make the time shorter and shorter, the velocity is changing, yes?
Yes.
In terms of the direction. So to get the instantaneous velocity, how do I get the velocity at this instant? How do I basically do it?
Do you just like make the B like on the A or something?
Yeah,
Like,
you're basically bringing the B closer and closer and closer and closer and closer to the A. So basically, velocity is calculated as change in displacement over change in time. Average velocity, as you've done before, is the total displacement over the total change in time.
Yep.
Instantaneous velocity is still change in displacement over change in time, but you're trying to make the change in time as small as possible.
Yep.
And formally, that is the limit as delta t approaches 0.
Yeah.
And that means in this context, we're basically bringing this second point as close to A as you can. That's really what we're doing. We're just bringing it closer and closer and closer to A. So essentially, we are bringing it basically on A. And so you're going to get this direction. Now, you may or may not remember back in year 11 that the definition of a derivative is f of, well, is f of x plus h minus f of x all over h, the limit as h approaches 0, which we can think of as this is a change in function. So you can think of it as a change in y over a change in x with a limit as the denominator, delta x approaches 0. And that is dy dx, right?
Yeah.
And that's why velocity, by definition, which you should also know from your 2-unit or 3-unit, is the derivative of displacement with respect to time.
Yeah.
Okay. So with that in mind, we've now basically revised and talked about how to work out the velocity at a particular instant at this point, right?
Yeah.
Now that is applicable in general, but let's consider a few things. This is circular motion. Is this a 1D or a 2D thing?
2, sorry.
Right, it's a 2D. You've got left, right involved and also up, down involved. So circular motion is a 2D motion. All right. Now that we've established that at A, it's going in that direction, let's now redraw it and think about this. If I've got a particle that's going clockwise, I can consider certain points. I'll just label them, say A, B, C, D. So at point A, it's going to have a velocity. What direction is the velocity at A?
Right.
Basically. What is the velocity at B? The direction.
Down. Down.
C.
Left.
And D.
Up.
Right. So for a circular motion, what can we say about the direction of the velocity?
Like the tangent, but like
Exactly.
like clockwise, wherever. Yeah.
Velocity is tangential. In the terms of the direction of the velocity, it is tangential. Now, circular motion only means it's going in a circle. So that means it can be speeding up. It could be slowing down as in terms of going around the circle. You can have a race car going around and it's going faster and faster and faster, or it can go slower and slower and slower. Those are all fine. Now we're going to simplify matters. For simplicity, assume speed is constant. So we're not moving faster or slower as we go around the circle. We're going to go at the same speed. Now, is the velocity the same as you go around the circle?
Yes. No, it's not.
Why
Because
not?
direction is different.
Exactly. Note, even though the speed is unchanging, even if speed is unchanged, velocity is a vector. And if it's a vector, it includes direction. And if it includes direction, and we've talked about at A, it's this, at B, it's this, at C, it's to the left, and D, it's upward, then it's very clearly changing direction.
Yeah.
For a particle to undergo circular motion, it must experience a change in direction. And therefore, velocity must change.
Yeah.
So if velocity is changing, as we have established, what must the particle be undergoing? What must it experience?
Acceleration.
Exactly. By definition, acceleration is a change in velocity over time.
Yeah.
Therefore, there must be acceleration. Must be.
Yeah.
All right. Now, we won't prove it to you just yet, but with this, can you see that from A to B, it's changed sort of to this direction? So it would sort of make sense to suggest that the acceleration could be in this direction. Does that make sense? Like it's going to head that way. And from B to C, it's kind of needs to head that way, and C to D kind of needs to head that way, and D to A kind of needs to head that way. So it's not completely like it's not it's reasonable based on what we've done so far. Like my suggestion of acceleration being those directions are reasonable suggestions. Does that make sense?
Yeah.
Right. And so here's the crux of the matter. For circular motion, you've got velocity is tangential, but you also experience acceleration. If acceleration is in the direction I've listed, which direction is that pointing? What would we call that?
The center.
Just towards the center. And there's a particular word for towards the center. Do you know what that is? Oh.
No idea.
Yep. So that we have acceleration is centripetal. Centripetal literally is just a word meaning towards the center. That's all it means.
Yeah. Yeah.
Now, because it's centripetal, we normally give it a subscript C. So this is the centripetal acceleration. And this is your velocity. So we've established that the velocity is always tangential. The acceleration is always centripetal, which means towards the center. So it will point towards some center O. Now, you may or may not be aware, you don't really do much circle geometry anymore, but if you're going towards the center, then that just means it's in the radial direction, like it's going in the sort of radius, right?
Yeah.
And the radius and the tangent are always perpendicular to each other. So those are facts that may be helpful to help your understanding. So the tangent of a circle, the tangent to a point on the circle is always going to be perpendicular to the radius, which means the radius is the normal, basically.
Yeah.
Okay. Right. Now, this centripetal acceleration for now, I'm just going to tell you, we'll prove it later, is equal to v squared over r, where v is the velocity in meters per second, and r is the radius. So the centripetal acceleration's magnitude is v squared over r, and that probably makes sense intuitively. If you've got something going around in a circle, the faster it goes around the circle, it's got to change direction more quickly, so the acceleration is bigger. If the circle is smaller in radius, then you have to change your direction faster as well, right?
Yeah.
And remember, this means it's centripetal, which means it's towards the center. All right. Now, for a particle to undergo circular motion, it must change velocity direction, which means it must experience that acceleration, which for now we've just told you what it is. But how does any particle get acceleration? How can any particle? Yeah, exactly. You need a force. So to undergo acceleration, force, more technically, can you be even more specific?
Non-zero.
Yeah, net force,
Net
non-zero net force is required. So if I've got some particle and it's undergoing this acceleration, what's the force I would need? How do I calculate it?
F equals ma.
Exactly. We call that Fc, centripetal force, is basically m times a, which is mac, which is therefore mv squared over r.
Yeah, sure.
So you have to pay very close attention to what this means. M is, I mean, obviously m is mass, so we'll quickly write it out, but m is mass in kilograms. V is velocity meters per second. R is radius of the circle in meters. So do pay attention to the fact it's SI units. That's probably not going to give you too much trouble. But pay close attention to what Fc is. Fc is the centripetal force
Yep.
in Newton. Now, is the centripetal force an actual force that exists?
Exists.
Like, is it like a force in its own right?
Probably not.
In other words, it's kind of like this, right? AC is the required acceleration. If you don't have AC, if it's AC has to be exactly v squared over r, to be clear. Okay, it could be big. If you have an acceleration that's bigger than v squared over r, then you're not undergoing in a circle. You'll be doing a spiral, in fact, right? So instead of going nicely around in a circle, I'll do this on the next page. If the AC is not equal to exactly AC, then you won't be going in a straight in a circle. If the acceleration experienced is greater than AC, that means you're going to spiral in towards the center.
Yeah.
If the A experienced is less than AC,
And it gets like bigger.
you're going to spiral out. Okay.
Yeah.
So that's why only if A equals AC, no more, no less, is a circle maintained.
Yeah.
Right.
Yeah.
Now, here, AC is the acceleration required. That means this is the force required. Yes?
Yes.
Just because you have require force doesn't mean you have it.
Probably not.
Basically, it's like this. What's something you want to buy?
I want to buy I don't know, some Travis Scott X Cause t-shirt, something like that.
Okay. And how much does that cost?
Oh, like 150, not that much.
150?
Yeah.
Okay. So you want to buy this t-shirt. It costs 150.
Yeah.
Doesn't mean you have 150?
No.
Right. The cost is the cost. Doesn't mean you have the money to buy it, but that's how much you need if you want it. Does that make sense?
Yeah, yeah.
The centripetal force is like the cost. If you want to go in a circle with these parameters, you need this force. That doesn't mean that force is there. That's the cost, right?
Yeah.
Now, on the other hand, if I see that you have the t-shirt and you didn't before, I can probably reasonably assume that you spent 150 to buy the t-shirt. Yes?
Yeah.
And how could you possibly have paid for that t-shirt? Like, give me some options.
PayPal,
Sure?
cash.
Sure?
Oh, wait, do you mean like methods, payment methods?
Yeah, exactly. You're on the right track. So you could have paid by cash, you could have paid by PayPal, you could have paid by credit card, you could have paid by Bitcoin if they accept it. But the point is the cost was 150, right?
Yeah.
But the cost itself is not money.
Yeah.
The cost itself is not a funding source, right?
Yeah.
Cash, PayPal, Bitcoin, bank statements, like bank savings, whatever. Those are actual funds, yes?
Yeah.
So your centripetal force is just a cost, but that force, if you want to go in a circle, needs to be provided by actual forces.
Yes.
Just like the cost of 150 for a t-shirt needs to be paid for by actual money sources. The cost is not a source of money. The cost is just the cost.
Yeah.
Make sense?
Yeah. Yeah.
And what are actual forces then? Give me some examples of actual forces.
Well, gravitational.
Exactly. It's all the stuff we did before. Gravitational force being weight, your tension force, your normal force. Those are your actual forces.
Yeah.
All right. So basically, recapping, the key concepts for circular motion are: if a particle undergoes circular motion, then velocity is tangential, acceleration is centripetal, otherwise known as towards center.
Yeah.
And this AC equals v squared over r. the required force is also centripetal, is also mv squared over r. And that's the key concept. Now, briefly expanding on this, you've done your work on sectors, arc lengths, right?
Yeah.
And so you understand that if you're starting from here, from A, and you're moving to some point P, then you've moved the distance of S, right?
Yeah.
So your S is your displacement. And we will calculate the velocity as delta S over delta T, or if you like, ds dt. And your acceleration is then the derivative of v with respect to t, if you like, right? It's change in v over change in t, right?
Yeah. Yeah.
Are you familiar with the concept of angular velocity and angular? Do you know what?
Angular, isn't that just like
Because you
velocity,
do
but like
engineering, right? So are you happy with angular velocity and so forth?
I'm not entirely sure what that means. Like,
Right.
what exactly? Yeah.
So it's actually really easy. So you understand that you, as the particle moves p, you're going to get this displacement, which we can calculate the velocity and the acceleration. Yes.
Yeah.
But sometimes we're not so much concerned with this distance, but we might be more concerned about the angle.
Yeah.
So basically, we're now measuring not so much how fast that moves in terms of distance, but it's really more like, for example, how fast do I need to turn my head, right?
Yeah.
Or if you're like thinking of sort of like, you're playing games. So if you're like thinking of how quickly I need to turn to aim my gun, right? Or artillery piece,
Yeah.
depending on what type of game you're playing. So that sometimes the angular velocity is more important to you, because if you're just a sniper and you're standing still, or if you're just a turret that can't, you're really worried about how quickly I need to turn my turret to fight in the right direction, rather than how the actual speed that person's running in that direction.
Yeah.
So this
Yeah.
is when we move from a linear system to an angular system. Angular focusing on angle. So theta is your angle. And then just like we've got a velocity, linear velocity, we've got an angular velocity.
Yeah.
Which is represented by the letter omega, angular velocity. And it's of course analogous, so it's just d theta dt. It's a derivative of theta with respect to t.
Yeah.
Have you done like angular acceleration as well in engineering?
Not at all.
Oh, okay. So there's angular acceleration, and then there's so there's also F equals ma, right, for linear.
Yeah.
There's also equivalent torque equals the inertial mass times the angular acceleration. Okay, so some of those you should have done in engineering at some point, but it sounds like you haven't done that yet. So we'll just focus on the two here that are important to us. So here's the thing. We understand that, well, how do we calculate velocity? Well, sorry, before we do velocity, how do we calculate this S? What's the relationship between S and theta?
You did the arc length formula, I guess.
Which is?
Which is arc length formula would be S equal to R and then times theta.
Where theta is in which? Theta here is in
Sorry? In radii. Not radian. Is in what's it called? Radian. Sorry.
So typically your SI units displaces it in meters. This is in meters per second, and this is in meters per second. Your SI unit for theta is in radian.
Yeah.
And this will be radian per second. So that's why this formula is more applicable to us. And so if we then derive S with respect to t, it will be deriving R theta with respect to t, right?
Yeah.
Now R for a circle, does R change?
No.
So therefore that will just be R times d theta dt. Agreed?
Yeah.
And therefore V equals R omega.
Yeah.
Right?
Yeah.
The SDT is V. D theta dt is omega.
Yes. Yeah.
So that means there's a relationship between, for a circle where the radius is constant, there's a relationship of v equals r omega between the linear velocity v and the angular velocity omega. Now,
Yeah.
sometimes often you'll be given questions in terms of v and r, but you may also be given questions in terms of omega. And so that's when these forms may be more useful.
Yeah.
All make sense?
Yeah.
Excellent. So when it comes to circular motion, the key concept, the fundamental key concept really is here. If a circle, something's undergoing circular motion, it's got to experience an acceleration equal to the central acceleration with this magnitude,
Yeah.
which means the necessary net force on that particle must be no more or less than the centripetal force required, which is mv squared over r or mr omega squared.
Yeah.
From then
Yeah.
on, every single thing you're doing really is just basically doing questions in terms of dynamics. So working out what the net force is, working out the directions, summing them up, like exactly what we did in term 2, except applying it to net force is no longer MA. Well, it is still MA as we were doing in term 2, but this A now is AC in the circular motion direction.
Yeah.
Good.
Yeah. Sure. Is it okay if we like go through like a sample question or something?
Of
So
course.
because sometimes when I learn theory and I go to the question, I kind of get stuck.
Yeah, so that's what we're doing next. Of course we're doing that. Yeah.